hydrolysis, the reaction of an ion with water to produce an acidic or basic solution. However, only some ions can undergo a hydrolysis. There's a whole bunch of them that don't, okay? So when you place a salt, which is of course an ionic compound, what is the first thing it does when it jumps into the water? It dissociates. And when it dissociates, it becomes its ion. So the first thing you're going to do with any compound is dissociate it into its ions so you can see the two different ones separately. Once it has dissociated, each of the ions may or may not undergo hydrolysis. Okay? So for all of these questions, the first thing you should be doing is you should be dissociating the compounds so you get the ions, and then the second thing you will do is you will look at the possible hydrolysis of the ions. So a solution is made containing the salt NaCl. Does hydrolysis occur, and is the resulting solution acidic, basic, or neutral? So when it dissociates, we get Na plus and Cl minus. Hopefully that is easy for you guys at this point. Do the ions hydrolyze? Na plus. Now remember, hydrolysis is the reaction of the ion with water. So you're going to put the ion with the water. You're going to see, will it accept a proton? Will it donate a proton? Or will it do neither? So if we put sodium with water and we say, what on earth do those two things do when they put it together? All done? Thank you. Can sodium accept a proton? Well, let's look at what that would look like if we did. If we had a hydrogen move from water over to sodium, now we would have two positive charges, and we would have an H. And what on earth is that thing? Yes? Like, that's just crazy. So no, we don't get that. That's no. Okay? If it looks too bizarre, it's not something, and it's not on a data sheet, then it's not something you need to deal with. Sodium doesn't have a hydrogen to donate, so it can't be a base, it can't accept one, it can't donate one, so it does not hydrolyze. Okay? And in fact, no metal ions hydrolyze except for 3 of them. Iron, aluminum, and chromium, and we'll talk about those a little bit more later on. Okay? So do the ions hydrolyze? We just dealt with the Na, and we said it did not hydrolyze, so there was no hydrolysis of the cation. So now we're going to look at the anion. We're going to look at our Cl, and we're going to put the ion with water, and I don't know why there's a question mark there. I think I was cutting and pasting and it just ended up there. So we're going to see, will it accept a proton, will it donate a proton, or will it do neither? Well, what do we get if we put Cl minus with H2O? Can it donate a proton? Cl minus? No, there is no proton. Has no H plus. Yes? So it cannot donate a proton. Can it accept a proton? Can we have a hydrogen do that? Well, if we put a hydrogen onto the chloride, we get HCl, and left over would be hydroxide. So far, so good? Okay. So it looks like chloride can accept a proton, but wait, there is a problem. And that problem is that HCl is a strong acid. It is up in that gray zone. And what kind of arrow do we have? We have a one-way arrow. So, is it possible for H plus to stick itself onto Cl minus? And the answer is no. Okay? So this cannot happen. I don't know if any of you remember, I gave away a pen to someone, that was my Proton, and then I couldn't take it back because I was too weak, right? And that's what chloride is like. It cannot take a hydrogen away from water because it is too weak of a base, okay? So as it turns out, none of the conjugate bases of the strong acid, so that would include the ClO4 minus, I minus, Br minus chloride, nitrate, and HSO4, none of them can hydrolyze. Now, I'm going to actually put a little exception here. HSO4 minus can actually donate a proton, but it cannot accept one, okay? Because it's got a hydrogen. Do you see how none of the rest of them have a hydrogen? So they would not be able to donate a hydrogen. But none of them can accept a hydrogen, and HSO4 follows that rule. And it makes me angry because otherwise this would be so easy to teach, but there's like an exception, and then there's an exception to the exception, and then that's never fun. But anyway. So since neither sodium nor chloride can hydrolyze, the salt is not producing, H3O plus, it's not producing OH minus, which means that it's going to be neutral. So if there is no hydrolysis, a solution will be neutral. And what pH are we at if the solution is neutral? pH is equal to 7. Okay, so remember, if we want to find the pH of any salt, we look at both ions, and I guess that would be a salt solution. Obviously, if it's not dissolved, it doesn't have any pH whatsoever. We have to look at both the cation and the anion. So let's start by focusing in on the cations. Whenever cations hydrolyze, they always form acidic solutions. So cations always form acidic solutions. And you don't have to memorize that, because if you look at the cations that do hydrolyze, they do it by giving away a hydrogen. Okay? So here are the 4 cations that do hydrolyze: ammonium, iron 3+, Al3+, and chromium. So iron, aluminum, and chromium. We know the name of ammonia, that's perfectly normal, okay? When we get to iron, it is one of those complex ions that I've mentioned previously in the course. It associates itself with 6 waters, and it is those waters that allow it to hydrolyze. The other ions, like sodium, does not have waters that attach itself. Calcium does not have waters that attach itself. Only those 3, okay? There might be others, but you don't need to know them for grade 12. You only need to know the 3 that are listed here. And how are you going to remember those 3? Well, this is a really stupid little mnemonic device, but it really helps. They're kind of weird, right? Because they're the only 3 metals that do it. And so they feel creepy because they're kind of, you know, a little weird. Okay, so they feel creepy. And then there's, of course, ammonium. And ammonium's just kind of its weird little thing. It's the only positive polyatomic ion. Okay, it's got hydrogen in it. Okay. Another way to remember it, if you don't like that feel creepy thing, you can look on your table, and on the acid table, you're going to look for the longest names. There are 3 really long names on your acid table. Do you see how these ones are like much longer than anything else? Yes? Those are your 3 cations that will hydrolyze. And then, of course, you just have to remember ammonium, okay? So here's the process by which they actually do it. You are not responsible for this. Of course, you're not responsible for anything right now, are you? You won't have a test on it. But that's okay. I'm going to put it down anyway. You're not responsible for knowing this. But sometimes it's just nice to see, okay, the iron has dissolved in the water, and now 6 waters attach themselves to the iron. And what does that look like? It's going to look something like this. And I don't know if you can see them, but there are lone pairs on the oxygens. I don't know if you remember the structure of water. If we were to draw a Lewis structure of water, oxygen has 2 lone pairs, and one of the lone pairs, each of those is attracted to that positively charged iron 3+, and so they form a loose bond, okay? And that's going to happen with the aluminum, those lone pairs, and the same thing is going to happen with the chromium. And just in case you're wondering, because if you do go on and take chemistry, these sort of like, these diagrams, if you see this kind of a thing, this means that the substance is coming out of the page. And if you have like this, that's going into the page. So if you look at that chromium structure, it's not a 2-dimensional structure, it's a chromium. Up above it, sticking straight up the top, is one of the waters. Coming out the bottom is one of the waters. And then the other waters are on a plane, 1 in front, 2 in front, and 2 behind, like a tutu around the middle. Yes? So we have a water on the top, a water on the bottom, and then the other 4 waters form a tutu around the middle. Okay, so that's what that structure is like. But you're not responsible for being able to draw those. However, knowing the fact that they make a tutu, that's a huge concept in first-year chem that I never understood my first year, even though it seemed really easy when I finally did learn it. All right, so now, why is it important that these waters be there? Well, if you're going to act as an acid, what do you need? You must have, oh, that's a bad pen to use. You must have hydrogens. Iron on its own does not have any hydrogens, but if we attach water to it, all of a sudden we have all sorts of lovely hydrogens. Okay? And so these ions can now act as acids. So here are the hydrogens that are going to be donated. So we are going to take one of the waters, and we're going to remove its hydrogen. If you remove a hydrogen from water, what do you get? hydroxide. So you'll notice that one of the waters has turned into hydroxide. Yeah? And we started out with 6 waters, but now we only have 5 waters, and the other one has turned into hydroxide. That hydrogen that came off is now part of the hydronium ion. Okay? Now, once again, do you need to memorize this? No, because if we go back here, or if you look on your data booklet, guess what? That equation is given to you. So as long as you remember that here we have iron and the entire equation is given there, then you can write the hydrolysis equation. Okay, you just need to add the water into that. Okay, so you can just look them up on the table. You do not need to memorize this because it is in your data table. Now, we can see that when the iron hydrolyzes, it produces H3O+. If it produces H3O+, what does that mean about the solution? The solution will it be acidic, basic, or neutral? Remember, hydronium is essentially the same as hydrogen, and so the solution will be acidic. So I could write out all of them, you know, the aluminum and the chromium, but the only thing we would do, this could be or aluminum or chromium. It's the same reaction for all of them, and you can look them all up on your data table. Okay, and then our only other one that we're left with is ammonium. And I'm hoping that you are familiar enough with ammonium that you will go and just, you know, look for it if you don't know what to do with it. Again, you can just look it up on your data table. You can say like, okay, ammonium. Oh, there it is right there. It becomes NH3 and it gives away a proton. So when it hydrolyzes, and remember, hydrolysis is the reaction of an ion with water. So if you're showing the hydrolysis, you can't do like the little cheat thing where you just take off the hydrogen. Like you could, it would not be okay to write NH4 plus gives NH3 plus H plus, because that's not showing the hydrolysis, which specifically says it has to be reacting with water. Yes, yes, of course. So ammonium produces H3O plus. If you have made H3O plus, are you acidic, basic, or neutral? If you make hydronium, you are acidic. Cationic hydrolysis always produces acidic solutions. Always acidic. Now, wouldn't it be lovely if anions always made basic solution? Ha ha ha. Wouldn't that be nice? However, no, they usually produce basic solutions, usually. Okay. However, some anions are amphiprotic, in which case you either get an acidic or a basic solution, you have to make a choice. Okay? So let's look at KF. First thing you're always going to do is write the dissociation. The second thing we're going to do is we're going to ask, does the cation hydrolyze? And if it's a cation, you have to ask yourself, is it ammonium or feel creepy? Yes? This is neither, K is neither ammonium nor is it FeAl or Cr, feel creepy. And therefore it will not hydrolyze. On the other hand, fluoride, we have to look at fluoride and say, does it hydrolyze? Well, if we put it with water, it can't give a proton, it has to accept a proton. It ain't got no proton to give. And it would become HF. In order to know if this happens or not, we need to ask, is HF strong or weak? So we have to go to our data booklet, unless you know it by heart. And here is HF, hydrofluoric acid. It is in the middle of the data table in the white section, so it is a weak acid. So is HF strong or weak? It is weak. And do weak things form equilibria? Weak things form equilibria. Do you remember the last time we had an ion? We had chloride, and we put it together with water, and we said, does it react to give me HCl and H3O plus? And we said no, because HCl is strong. HCl would just push that reaction that way and would say, no, you cannot go forward. Yeah? However, HF is weak. So can we make HF? We sure can. And if we can make HF, then hydrolysis does occur. Okay, so we're going to look at what is produced. So if you look at something and you say, yes, I have hydrolysis, you need to say, did I produce hydronium or did I produce hydroxide? Well, let's look at our reaction. We produced hydroxide, and therefore the solution will be, is it going to be acidic or basic if we produced hydroxide? Basic, okay? So if we produce hydroxide, the solution is going to be basic. Now, for just the moment, we're going to assume that the cation does not hydrolyze, okay? And if that's the case, we can just focus on the anion, okay? Because we need to do a little bit more work on anions. If the conjugate acid of the anion is weak, you will get hydrolysis, and the solution will be basic. If the conjugate acid of the anion is strong, you will not get hydrolysis, and the solution will be neutral. So looking at NaCN, first thing you do, right, the dissociation. So you can see, who are my ions? I get Na plus and I get Cn minus. Then you're going to look at the cation and say, does it hydrolyze? Does it react with water? And the answer is no, because Na is not NH4, it's not iron, it's not aluminum, it's not chromium, it's not feeling creepy, okay? Feel creepy. Does Cn minus hydrolyze? Well, what you can do is you can write it out. You can say, okay, if I put Cn with water, it has to have accepted a proton, and we formed an acid, HCN. Once you find that acid, you have to ask, is it strong or is it weak? Go to your data table. Let's take a look. I think it's, where is it? If you know your strong acids, it's actually like a nice thing because then you don't have to go rummaging around on your table quite so much. Where is my HCN? Come on now. There it is. Oh, I've got like red things around it. Okay. That's probably why I couldn't find it. There's our HCN. It is a weak acid. If it is weak, does that reaction take place? Does that hydrolysis take place? Yes. Okay, so we say yes, this happens. And once it happens, you have to say, does it make hydronium or does it make hydroxide? This one makes hydroxide. And if it makes hydroxide, it is going to be basic. What can you say about the pH if it's basic? The pH is? What's a basic pH? Greater than 7. Just a quick little reminder there, you know, for Unit 4 test stuff there. Basic pH is greater than 7 unless you're at a temperature other than 25 degrees, right? Okay. Oh, and by the way, on that pH quiz, if any of you noticed that question about the temperature of water was a little bit like weird, that's because it was supposed to be times 10 to the minus 14, not times 10 to the minus 4. So you ended up with like extremely high ion concentrations, and that might have looked a little weird to some of you if you were paying attention. Anyway, write the dissociation of the ions. So now we're looking at calcium bromide. Calcium, does calcium hydrolyze? Try to do it without looking. Does calcium hydrolyze? What do you ask yourself for a cation? Is it one of 4 things? What are those 4 things? Ammonium, NH4, Fe, Al, Cr, Feel, creepy, and ammonium. Okay? So it's not one of those things, so no, calcium will not hydrolyze. How about bromide? When we look at the anion, what do we need to ask ourselves? We ask ourselves, is the conjugate acid strong or weak? Is the conjugate acid of Br minus strong or weak? And it is HBr. And you can go and you can say, oh, look, there is HBr. It is strong. If it is strong, do we get hydrolysis of bromide? No, it does not react with water. And if calcium doesn't react and bromide doesn't react, what's the pH of the solution? 7. Okay. Okay, SrNO2. I'm going to just write it over on the side. SrNO2. Are you guys doing chemistry or are you goofing around? These guys here. Jake and Sean, are you guys doing chemistry? They have no idea. Are you doing chemistry or are you goofing around? Do something on chemistry. Be reviewing for something or be paying attention here. Do something chemistry. Okay? Yeah. Yes, of course. Either you're going to do fantastic on that Unit 4 test next week, or you're going to learn some of this, or maybe both. I don't know, but it's got to be one of those things. Okay? All right. Does strontium hydrolyze? How do you know for a cation? Is it feeling creepy? Or is it ammonium? And the answer is no. And if this answer is no, then this answer is no. How about NO2? Does NO2 hydrolyze? So for positive ions, we ask ourselves, is it one of these four? If it's not, it does not hydrolyze. What do we ask ourselves for the anions? Yeah, we ask if the conjugate acid is strong or weak. And if we go and look up HNO2, there we go. 4.6 times 10 to the minus 4. That is a weak acid. Okay. And if it's a weak, if the conjugate acid HNO2 is weak, then we say yes. If it were strong, we would say no. And if it does hydrolyze, you can write the hydrolysis equation. NO2 minus. What do we have to react NO2 minus with to write the hydrolysis equation? We have to put it with H2O. And NO2 has to accept a proton, leaving behind an OH minus. And if that's what we end up with, remember SR2 plus did not hydrolyze, NO2 minus did. So the only thing we have in there that's going to affect the pH is that OH minus. And so is this acidic, basic, or neutral? It is a basic solution. Okie dokie. And I feel like that might be a good breaking point for today. So you could, like, I don't want to, because people seem to be working on lots of things, and I'd like to come around and answer questions too. Like I said, I'm probably not going to make anyone perfectly happy, but hopefully